Hi, uh, in this video I will demonstrate the basic usage of a research tool called QwalKeko. You can find it on GitHub if you follow this link. What you first of all need is an Eclipse. I suggest starting with a fresh copy so that you don't mess up your own Eclipse. What we have here is a fresh install. In case you want to install it yourself, you can just follow the installation instructions, which boil down to cloning 3 repositories and importing them in Eclipse, as well as downloading 2 plugins. Once you have done that, you should have something that looks like this. The final part you have to verify is that in git commands.java that this part, this variable points to the installation of Git. If you have done all that, you can right-click on the QwalKeko project and debug it as an Eclipse application. So once you've done that, you get a new Eclipse that is running our plugin. You'll notice that you have no projects here. So the first thing you'll have to do is to import a new project that we want to query. For this, you go to the menu, you import a Git repository. And so here we have, I will be using the Atlas project, and you select the .git folder and you open it. What should happen is that a new project is added that contains a large XML file. So here's a project, I'll open it, and it contains one XML file. Next, you have to tell QwalKeko that you want to create this project. And so what you do is you go to configure, you add the history nature to the project, and you include it in the queries. So now if you refresh project, you will notice that it has copied the Git repository. So if you use it on live code, then QwalKeko will not mess up your own repository, but it will use a copy of it. Next we want to start a REPL, which here. I will go back to the original Eclipse. Where now you see this, you can click it and you get a closure REPL. So this thing works. And now what you want to do is you need to go to the demo folder if you want to do the demo for ICSME. You open it. You can also find, for example, the Atlas repository that I'm using. You can find it here. You right click and you say load file in REPL. Once everything is loaded, you switch to the namespace, and so now we're in this namespace, and I will just go over what we're trying to do here. So what we're doing in this experiment is classifying changes that are made to Selenium files. Selenium is a testing framework for your browser in which you can script, for example, a Firefox browser to take certain steps, and you validate that, for example, the title bar contains a specific string, etc. So the first thing we need to do is to construct a graph, and so to this end we will take we will ask QwalKeko all the project models. There should be only one, because that's this thing here, and we will convert it to a graph. And so we define a model, we define a graph. So now if we look at a graph, we get the atlas graph, and we will also take the very first revision as the root. Then, just for the purpose of the demo, I will only take the 51st versions so that the query don't take as long. So the first step we have to do is we will want to identify all the Selenium files in the project. So to this end, we say that a file is a Selenium file if it imports a package that contains the string .selenium. So we have defined a predicate for that. What this thing does, it will verify that CU is a compilation unit, that this compilation unit has one import statement of which the name contains .selenium. So we will define it. And we want to do this for every version in our graph. And so for this we have this part. So what we do is we will apply a function over all the versions in our graph. And for every version this part of code will be executed. What it does is it will launch a QwalKeko query that will return so an info object which basically contains the path to a file, a compilation unit of that file, and in which version we find the file. We will do our query on our graph. We will start in a specific version, so in the versions we're giving it. We will end in the same version actually. We do not introduce any new variables, and then for what we will do is we will take an added file. If there are no added files or newly added files in this version, this thing will fail and we won't do anything else. And if there are files added, we will check out the code of that revision. We will find the corresponding compilation unit of that file and we'll verify whether it's a Selenium compilation unit. And so we will do that. This will take a couple of minutes, so I suggest that you go and take a cup of coffee, and I will see you afterwards. So we're back. Our query is finished. It actually took only a minute or two. So what we have now are a bunch of results. If we inspect those, I'll just take the first of results. What you get is a lot. Is a file, so visualize top 10 expressions level.java, which has been added, and you get the code itself. So here we see that this thing is a Selenium test, and we also get in which revision it was found. And I scrolled up too much because I was showing multiple things. So now we know all the Selenium files in our 50 revisions. For the experiments that we took, that we did, we actually wrote those to a database so that we don't have to recompute them every time. For this demo, I'll just keep them in memory. Then we want to define a new predicate that says whether a file is a Selenium file. Something is a Selenium file in case we find so this file is a Selenium file if one of the results one of the files in our results has the same path as the file we were giving this. So that's what we do here. We take the path, we filter out all the files that have the same path from our results, and if this amount is larger than 0, then we know that this thing is a Selenium file. So let's do this code, and then we want to compute changes made to this file so that we can classify them. And so for this we once again map something over all the versions in our graph. What we map is this part, and so what we do is we are interested in the two compilation units, one prior to the changes and one with the changes applied to it. We want to know the file, we want to know the revision, and we actually want to have the changes made to the compilation units as well. And so we start in a version, we will end in a different version. And what we do is we are looking for a file that has been modified, and this file also needs to be a Selenium file. If that's the case, we will find the compilation unit of the file by checking out the source code. Then we make use of a call operator that moves us back to the graph, so we go to a previous revision that contains the original source code, and of that revision we will find the same compilation unit that we did over here, but then it will be the previous version, so prior to the changes made. And then we make use of the predicate change that will bind the variable change to a single change made to the compilation unit, and this thing will be returned as a result. And so the result of this function will be all the changes made to every Selenium file in our Atlas project. So let's evaluate this. Let's evaluate this. Let's print it, because closure is lazily evaluated, and if you don't print it, then it won't do anything. So we're back with our results. So now we have a bunch of changes. If we inspect one of these, we should get two files, the path of the file, the version, and a change object. Inspecting this, okay, apparently it's a dummy service that got changed, and if we see our change operation is a deletion of some Java doc. Not the most interesting change, but a change nonetheless. So what we can now do with these changes is to classify them. And so here's a small example. We are interested in changes made to the locators. In Selenium you have to find elements in your DOM tree. You can do that in two ways. Either you have a method invocation that is find something by, and then you give it how it has to find it. So we are looking for changes made to these method invocations, or a second way is to have an annotation that you can place on a variable, the add find by, and then that variable will be instantiated with the result of that find by. And so we are basically looking for a method invocation that has a certain name, and this name is by, or we're looking for an annotation that has a name, and the name has to be find by. We categorize our change by seeing whether a specific change affects a node. So what this thing does, it will look at the change and it will look in both the original and the target's source code of the change, so the original version and the modified version, and we'll just look in the modified AST node, loop to its parents, and bind each parent to its second argument, so find by, and if this thing ever becomes either the method invocation or an annotation, then we say that this change is a modification made to a locator. And so we have several more of these that we've used throughout the paper. You can find them in the experiments folder. And here you have Selenium, which contains the source code of our experiments. And here you have several classifications that you can check out. So this has been a short demonstration of QwalKeko and what it can do. I hope you've enjoyed it. In case you have questions, you can always contact me. Well, that's it.